Welcome to this module. In this video, I'm going to share with you some interesting facts about klystron. Klystron is one type of microtubes. Microtubes are designed to overcome the principal limitations of conventional negative grid electron tubes. In microtubes, the electron transit time is utilized for micro oscillations or amplification. So the principle uses an electron beam on which space charge waves interact with the electromagnetic fields in the microcavities to transfer energy to the output circuit of the cavity. So klystron is a most widely used tube amplifier at microfrequencies. Klystron works on the principle of velocity and current modulation, and there are basically two configurations of klystron tubes. One is two cavity klystron. It is used as a low power micro power amplifier, and the reflex klystron is used as low power micro oscillator. Okay. Now let us see the principle of two cavity klystron. A two cavity klystron amplifier consists of a cathode of focusing electrodes, two buncher grids separated by a very small distance, forming a gap of two catcher grids with a small gap B followed by a collector. The cavity close to the cathode is known as the buncher cavity or input cavity, which velocity modulates the electron beam. The other cavity is called the catcher cavity or output cavity. It catches the energy from the bunched electron beam. So the variation in the velocity of electrons while moving inside the tube is known as the velocity modulation, and this velocity modulation permits bunching of electrons while propagation. So the combined energy of bunched electrons is transferred at the output, thereby providing an amplified signal. So this diagram shows the structure of the two cavity klystron. As we can see in the above figure, it consists of two cavities called buncher cavity and catcher cavity. The RF signal to be amplified is provided at the buncher cavity. So the electron gun comprises cathode, heating element and anode. The electron beam is produced by the cathode by making use of the heating element, and the high positive potential at the anode provides required acceleration to the electron beam initially. And the region between two cavities is known as the drift space. To allow focused propagation of the electron beam inside the tube, an external electromagnetic winding is used that generates a longitudinal magnetic field. This is done in order to prevent the spreading of the beam inside the tube. The amplified RF signal is achieved at the catcher cavity. Also, a collector is present near the second cavity that collects the electron bunch. Initially, electrons are emitted from the electron gun, and the anode present in the structure provides the desired acceleration to the beam. In the absence of any RF input, the electron will tend to move with their respective uniform velocities to reach the catcher cavity and gets collected at the collector. But when external RF signal is applied at the input of the buncher cavity, and then this causes the generation of the local electric field inside the tube. This electric field causes the bunching of electrons as the field applies acceleration and deceleration to the moving electron according to the polarity of the signal by which the field is generated. Basically, the reason for causing the acceleration and deceleration is that when the direction of the movement of electrons is opposite to the direction of the field, then in this case, the electrons experience a decrease in their moving velocity. However, if the generated electric field and the direction of movement of the electron are same, then in this case, the electrons experience increase in the velocity of their movement. Now, let us understand in detail how this increase and decrease in velocity causes bunching of electrons. When negative half of the RF signal is provided as input to the buncher cavity, then the moving electrons experience a repulsive force due to the presence of the negative charge at the entering plate of the buncher cavity. As you can see in this figure, or we can say that due to the negative half of the input, the generated field will be in a direction opposite to the direction of the movement of electrons. So because of the opposition offered by the field, the moving velocity of electrons get reduced. Further, when positive half of the RF signal is provided, then the positive potential at the first plate of the cavity applies attractive force to the moving electrons. More simply, for the positive half cycle of the input, the generated electric field will be in a direction similar to the direction of the electron movement. Right. So this leads to an increase in the moving of electrons or moving velocity of electrons. Thus, combinedly, when we consider both cases, then the electrons that were emitted earlier by the gun will be decelerated. and while the electrons emitted later will be accelerated, thus all electrons while moving with the different velocities get bunched into the drift space. So this change in the velocity of electrons while moving due to the RF input is known as the velocity modulation. Once the electron bunching is done, and then the catcher cavity present at the another end of the tube absorbs the beam energy. And it is to be noted that to find the position of the catcher cavity, transit time of the bunches must be considered. This is so because the catcher cavity must be present at a sufficient distance from the buncher cavity so that bunching can be attained in the drift space. Further, once the energy is transferred to the catcher cavity, then electrons gets collected at the collector. So this is the applied diagram of reflux klystron amplifier. And this electron is, for example, suppose for example, when an input is applied to the buncher cavity, an electron A will pass the gap A at the time, and the voltage across this gap is 0 and going positive. Let this be the reference electron Y, and this reference electron is unaffected by the gap, and thus it can be shown that with the same slope of the applied diagram, this figure like this figure, as electrons passing the gap before any signal was applied to the bunching cavity. So electron, say for example, electron Z passes the gap A slightly later than Y. In the absence of gap voltage, both electrons would have continued past the gap with unchanged velocity. In presence of the positive voltage cross gap A, however, electron Z is accelerated slightly, and given enough time will catch up with the reference electron easily before gap B is approached. So similarly, electron X passes through gap A slightly before the reference electrons and is retarded by the negative voltage. At that instant across the gap, since the electron Y was not so retarded, it has an excellent chance of catching electron X before gap B, and this is shown in this applied diagram. And as a result of these actions, the electrons gradually bunch together as they travel down the drift space. The variation in electron velocity in the drift space is known as velocity modulation, as I said earlier, and the density of electrons in the second cavity gap varies cyclically with time. Such velocity modulation is not sufficient in itself for amplification by klystron, while bunching of electrons it exchanges energy with the slower electrons, giving it some excess energy, and the two bunch together move with the average velocity of the beam. So as the beam progresses further down along the drift space, the bunching becomes more complete as more and more faster electrons catch up with the bunches ahead. So eventually, the current passes the catch gap with a quite pronounced bunches, and therefore it varies cyclically with time, and this variation in current density enables the klystron to have a significant gain. Applied diagram shows that the bunching can occur at only per cycle, centering at the reference electrons, and the limit of bunching are also shown, and any electron arriving after the second limit were not accelerated sufficiently to catch up with any electron passing through the gap A just before the first limit. So bunches therefore arrive at the catcher grid once per cycle and then deliver their energy to the cavity. The catcher cavity is excited into oscillations at its resonant frequency, and a large sinusoidal output can be obtained because of flywheel effect of the output resonator. Bunching therefore depends upon the following parameters, like drift space should be adjusted properly, signal amplitude should be such that proper bunching takes place, and the DC anode voltage. So these are three factors when properly adjusted will give you the maximum efficiency. Okay. And the main applications of cavity electrons are, and the two cavity electrons will find applications in satellite communication, UHF, TV transmitters, as well as radar systems, and wideband high power communication and troposphere. And it can also be used as scatter transmitters. Now let us see the beam focusing concept of klystron amplifier. The klystron action depends on the long thin electron beam through the interaction region, because electrons carry negative electric charges, and however they tend to repel each other, causing the beam to spread. So a magnetic field parallel to the electron path is used to overcome the beam spreading. In low power klystrons, a series of small permanent magnets, each forming a magnetic lens, is placed along the electron path. That you can see in this figure. Right. And for these cases, the DC solenoid coil is wrapped around the interaction space or electron path. So klystron magnets are usually called focusing elements. Loss of magnetic field can be disastrous. In cases where the focusing element is an electromagnet, sensing circuitry is usually provided to rapidly shut down the klystron in the event magnet is lost or other faults cause the loss of magnetic field. Usually the klystron is a narrow bandwidth device because of the need of the cavity resonators. If all cavities are tuned to the same frequency, a condition called synchronous tuning, the bandwidth will be of the order of 0.25 or 0.25% to 0.50%. For example, a 5 GHz klystron that is synchronously tuned and has a 0.25 bandwidth requires input signal within plus or minus 6.25 megahertz spread of 5000 megahertz. So finally, it is possible to build a klystron with variable frequency tuning. All tuning methods involve varying the cavity dimensions. It is, for example, it is possible to design a flexible cavity wall of synchronously tuned klystron to provide a 2 to 3% tuning range. Unfortunately, flexible wall cavities have a limited service life, and another method to insert a capacitive paddle into each cavity. 10 to 20% tuning range is achieved, but a loss of efficiency on the low frequency end of the range. So finally, a sliding contact cavity wall will provide 10 to 15% of tuning range at the cost of mechanical complexity. Thank you.